Abinaya, working as a staff engineer at Freshworks, which is a multi-product SaaS company that offers sales, support, and marketing solutions at scale. So this visual that you see shows a comprehensive list of various Freshworks products and solutions, where I belong in the Neo platform service, and I lead a platform service named Unified Customer Record, UCR, which is a Freshworks native CDP, a customer data platform that holds several customer information and powers the core functionalities of various different products in the Freshworks product suite. And hence, one can imagine the kind of data volume and the criticality that is associated with such an application, right? Because if there is a service disruption in UCR, it can affect the ticketing support system in Freshdesk, conversational support in Chat, segments and journeys in Freshmarketer, and so on. And hence, it brings a significant impact on multiple products. And so this is a P0 service. And this P0 service is backed by Cassandra as its backend data store. So as with any production system, one might want to reevaluate their data storage solutions for reasons like cost, compliance, varying business needs, performance, scalability, etc. So for similar such reasons, we wanted to migrate our Cassandra solution to a serverless offering, our existing Cassandra solution to a serverless offering by DataStax. And in this session, we'll be going through this journey of data migrations, where we navigated the complexities of moving over billions of records across different data centers. And we'll also be exploring various tools and strategies that were key to our successful transition and all our learnings along the way. So these are the migration guiding principles that we started with. Firstly, zero downtime. We just discussed the need for it. Secondly, data integrity. Multiple different products have to share and access the same consistent view of data. And hence, it is very crucial to ensure data integrity throughout. Importantly, the customer should never notice, right? So we can't compromise on the application functionality or the performance. And these guiding principles help shape several decision-making during the course of our migration. So online migrations, right? These are migrations without downtime. And hence, in order to ensure the operational continuity, it is important to manage the live traffic, the incoming live request to the application effectively while the migration is running in parallel in the background, right? And in order to address the live traffic, we use the dual writes methodology, where every single write request from the application is broadcasted to both the source and the target cluster simultaneously. That is in real time, or at least near real time. That way the two databases are always in sync and consistent with each other. That way when the target database becomes fully operational, the switch from source to target becomes very quick and seamless as well. And as the dual writes are happening, we then trigger the migration job, that is backfilling of all the old data to copy the existing data from the source cluster into the target cluster. So that is what we term as historical data migration. So this is how it looks like, where the application reads from the source cluster but writes to both the source and the target, while we have the historical data migrator, the migration job triggered, which will copy all of the existing records and dump it all into the target cluster. So here we are covering two important phases, which is the live traffic handling and the actual data migration. So next we'll be talking about those options that were available to implement these two phases and how we narrow down to select the right tool that best suited our requirements. So the first thing is dual writes, where you want to transmit the data to both the source and the target cluster. So the most obvious approach here is to modify the application to do the dual writes, right? But it can be very complex in terms of code, maintenance, and very time consuming. Importantly, the testing can be very tricky here. And the next is CDC, where if your application already uses Kafka streams, or if the Cassandra cluster already has CDC capabilities, then you might just run the consumers to consume the updates from source and then relay it to the target cluster. But again, here the problem of consumer lag management remained, which meant that we have to take a short downtime. That is, just before switching from source to target, we would have to take a short downtime until the lag is fully cleared. So this brought us to this third option of implementing the middleware or a proxy layer where we hosted a separate proxy service. This served as an intermediate layer between the application and the database clusters. And we used an open source tool named ZDM that was available for Cassandra to implement this particular proxy layer. So the application, instead of talking to the databases directly, application will be talking to the proxy, which in turn will be routing all the read and write operations to the appropriate clusters, right? So this proxy, although it incurred the overhead of setting up additional infrastructure, it was still quite beneficial for two main reasons. One, it abstracts all of the code complexities of doing the dual writes from the application. Secondly, and most importantly, this proxy was highly configurable in the fact that it can be configured to direct the read and write operations specifically to the source or target or both. And this external flexible switch can be very beneficial during several phases of the migration. For example, when you finally want to switch all the read-write traffic to target, or if something goes wrong in the target and you want to switch back to source, during the entire course of the migration, whenever you want to toggle the switch between source and target for the reads and writes, it becomes very flexible because all it requires is the configuration and deployment of this proxy layer without having to touch the application. You don't have to redeploy the application. So this external switch was anytime our option for go-to writes. Our go-to option for the dual writes. And then similarly, we had quite some options for the historical data migration as well. The first one is the Cassandra native SS table loader, which just ships by default with every Cassandra installation. This uses a streaming protocol to copy all of the existing SS tables from one database to another. Basically, it uses a backdoor to copy all the snapshots. But this was not scaling well for large production workloads. So second option was the DataStax bulk migrator, right? So this, unlike the SS table loader, it uses the actual read-write path, and it was performing much better than the SS table loader, but again suitable only for small production workloads. So that brought us to this third option which we opted, which is a Spark migrator, right? So this Spark migrator uses the Cassandra Spark connector, which in turn uses the Apache Spark's capabilities to do the entire data transfer in a distributed fashion. And again, here we used an open source tool called the Cassandra Data Migrator, which we then have to customize it according to our needs. So we had to set up a whole different Spark cluster for executing this migration, where you have a master node and a bunch of different nodes. So this master node runs a driver program that will basically split the entire migration task into smaller chunks and distribute it across to the worker nodes. So the entire migration job is executed in this fashion. In Cassandra, if you see, the entire partition token range, it spans from minus 2 power 63 to 2 power 63 minus 1. This is the entire token range. The partitions within this range is what we actually want to migrate. So what this Spark migrator does, or the driver program does, is that it breaks the entire token range into chunks of smaller token ranges and assigns it to the worker nodes. Now, every worker node will then fetch all of those, based on the assigned token range, it will fetch all of those partitions from the source cluster and then copy it all to the target cluster. This is how the entire migration job is executed. And any data migration, again, cannot be considered complete without a verification phase. We want to validate whether we did it all right, that is, copied all the data from source to target. So that brings the need for a validation job. So this validation job is just yet another Spark job that operates in a similar manner as that of the migration job, where the entire token range is split into chunks. Here, the worker node reads from the source cluster, reads the corresponding records from the target cluster, does a one-by-one comparison to log all the discrepancies. And this can also be chosen to run in autocorrect mode, where you can just correct the discrepancies right away as you run the validation job. And this was also one of the other reasons why we chose this option, because this possibility of running a full comprehensive scan across the database was not available with the other two options. Of course, with the DataStax bulk migrator, this was still possible, but only account validation can be run there. That is, if you want to cross-check the count of records between source and target, it was possible, but this full comprehensive scan, we wanted to do a precise row-wise, column-wise value match. That was possible only with the Spark migrator. So having covered the two most important phases of this migration, I now want to step into an important section where we spend the majority of our work and time. These actually made the actual production migration fairly more straightforward, because these preparatory activities laid the groundwork or the foundation for that smooth transition in production. So the first one, so throughout this migration process, right, up until the final cutover, the application or the application is going to be dependent on the source cluster. And based on the option that we just chose, which is a Spark migrator, it is very clear that we are going to put some additional stress on the source cluster, because it is going to read from the source cluster and then copy it to the target. So in addition to the reads and writes that is done by the application, the migrator is also going to incur some additional reads on the source cluster. So it is very important to understand the source cluster capacity so that we know what is the leeway or the offset that is left and can be utilized by the migration job, right? So analyzing the past trends, such as the different traffic patterns, the nature of spikes, how the application behaves during the times of spikes, what is the maximum RPM that we can go up to with the source cluster without compromising the latencies, and what is the acceptable range of latencies without causing a timeout in the application. So gathering such information was very crucial in determining whether we have to expand the source cluster capacity ahead of the migration. Secondly, we run several performance and the load tests on the target cluster in order to ensure that it meets all the performance and scaling requirements that we intended to solve. Next, we ensure that our application has enough number of retries in place in case of timeouts wherever possible, because during the course of migration, anytime there can occur unanticipated spikes and occasional timeouts as well. So even in case of timeouts, we don't really want the application to suffer, right? And hence the need for retries, again aligning with one of our migration guiding principles. The next important pre-migration activity we performed is about gathering those data statistics, importantly the data volume, which improves the predictability of the entire migration process in terms of time, right? Because every single time we were able to precisely jot down the time that it will take for the migration phase, validation phase, when potentially the cutover can happen. We were able to precisely jot down all of this ahead of the migration. And more or less the planned and the actual timelines were almost always in sync, right? And gathering such data statistics not only helps with the timeline estimation, but also helps in fine-tuning various other migration parameters that we will be talking about, for example, the speed of migration, the batch read size, etc. And testing, again, so not everything can be tested in the lower environment. Although we did quite some amount of testing in the lower environment, not everything can be tested there because of the sheer difference in terms of the data volume, the nature of data, and importantly the traffic patterns. So we chose to do the actual testing in production, against production, where we employed a 10% migration strategy, and we tested all of the migration configurations, again 10% of the total data volume. Okay, and when I say 10%, it is not any random 10%. When the migrator splits this entire token range into smaller chunks, we try and migrate the 10% of every chunk. So that adds up to the 10% of the total data volume. And why do we do this? This is deliberately done in order to scan various segments of the entire token range in order to detect any uncompacted large partitions that may be dispersed across this entire range. Because presence of such partitions were known to cause downtime. Also, it can cause the entire migration process to halt in between, and it can cause increased spikes in latencies and timeouts as well. So again, aligning with aligning with the previous point, we made it a point to inspect the SS table metadata prior to the migration to understand the distribution of partitions, what is the maximum row size, or what is the maximum number of columns per row, what are the different tables that have the highest number of SS tables, and so on. Okay, because looking for such abnormalities helps prevent any adversities in production. And then last but non-negotiable step is to set up the observability for the application and as well as the database clusters, because this helps track the health and the progress of the entire migration. Importantly, it kind of reaffirms that we are going in the right direction and it is all working fine, right? Because any alert here calls us to make an immediate corrective action. Now we'll quickly go through an overview of the entire migration process before we delve further. The first step here is, of course, the pre-migration activities, and followed by the the dual write setup, where we handle the live traffic or transmitting the all the write operations to both the source and target, followed by the migration phase, where we migrate all the data from source to target. And then the validation phase, we may choose to run multiple iterative rounds of validation here until we are confident that the two databases are in sync. And once we have that confidence, we then proceed into the final important step of switching to target for reads. So at this point, the application is dependent on the target cluster for both read and write. The dual write is still happening, but the application is dependent on the target cluster. So this is just done by deploying the proxy layer. We don't have to touch the application here. And if everything goes well, then we continue to monitor the target for some time to ensure that everything is working as expected. And if at all we find any discrepancies, any issues in the target cluster, then we do have the rollback plan to switch back to source. So at this point, there is still no data loss because the dual writes is still happening at this point, right? And if you see step 5 and step 6 only involves the deployment of the proxy layer, no changes in the application yet. But if everything all goes well, then we go to the final step and cut off the dual writes from source. Meaning, we withdraw the proxy layer, point the application directly to the target database for all the read and write operations. So this gives an overview of the entire migration process. But again, there were some critical challenges and considerations that were associated with some of these phases, which we'll be talking now. So the first thing consideration was with respect to the dual writes or the proxy layer, where any downtime in proxy means a downtime in the application because the application is dependent on the proxy the whole time. So we have to ensure high availability for this proxy layer to prevent any single point of failure. Secondly, this is a new infrastructure component that we are introducing in the system, and hence it also needs to have the relevant dashboards and alerts in place, because specific statistics on these dashboards like throughput and latency can give a very clear picture of how the application is actually performing in the presence of this new proxy layer, right? So this was very important phase. And then coming to the migration phase, where we have to fine-tune a bunch of different migration parameters before we trigger the migration job, right? Because these were crucial in determining the smooth continuation of the application. So the first migration parameter here is a migration rate limit, which basically determines the speed of the migration. So the time taken for a migration is generally a factor of the data volume and this migration speed, the rate at which you do the reads from the source cluster. And hence, this migration rate limit had to be derived prior to the migration process, and this number is again derived by the 10% testing methodology that we just spoke. So we already know the capacity of the source cluster. So we do know the initial threshold value, that is the migration RPM that we can run this migration at. So we start with this initial threshold value, and then we go up incrementally as we monitor the cluster performance. Okay, but in general, we prefer to keep a lower number for this migration rate limit in order to accommodate any spikes that can occur in the production system. The catch here, however, is to strike a balance between the speed of the migration and the cluster performance. The second most important migration parameter was the batch read size. That is, this indicates a total number of reads that can be done in the source cluster at once. How many records that you can fetch from the source cluster at once. That is what this batch size is. And this batch size, if it is too small, of course, it affects the overall efficiency of the migration. And if it is too large, you're consuming too many records at once, and hence more CPU, and thereby increased spikes in latencies. And hence, we have to derive an optimal value for this split size. So this value for split size, it depends on the nature of data. So for most of the tables, a value of 1000 generally worked fine. But for some tables where there are complex data types like UDTs, collections, and for those tables with large number of columns, right, naturally the per record size of these tables will be very high. And hence the number of records that you fetch at once from the source cluster has to be lesser. And that is how we derive this batch size, and this has to be specifically determined for each and every table, and it cannot be common across different tables. Next one is the number of splits. That is, when the Spark migrator divides it into multiple token ranges, what is the optimal value or the right value of the number of splits that we can have? So that basically depends on this batch size that we just arrived and the data volume that we derived as part of the pre-migration activity. So if we can precisely know the count of records or an approximate count of records ahead, then that helps determining a right value for the split size, because the split size is actually a function of the number of records and the batch size, and this derivation just worked fine for tables of varying sizes. So these are the different migration parameters, and one important aspect in the migration phase, apart from tuning the migration parameters, is about this race condition, where the target, so the migration job is writing to the target cluster, the application is also writing to the target cluster. Now, what if both are writing to the same record at the same time? Then one of these writes will override the other. So we have to persist the latest version of that record in the database. So in Cassandra, in generally, the latest version is fetched based on the write timestamps. Right? So in order for the migration job to not overwrite the one that is done by the live request, we feed an input parameter, which is the migration start timestamp, as the value for the migration job. So all the writes done by the migration job will bear this timestamp, and any live requests that happen henceforth will have higher precedence because it will be done with the latest timestamp. And the next one is, of course, the Spark cluster tuning that we just set up, and it involves configuring, fine-tuning the number of executors that we want to have, driver memory, executor memory, but it all depends on the nature of Spark job and a one-time activity. Moving on to the considerations in the validation phase. So in the validation phase, we applied an optimization here to optimize the overall time taken. This is because the time it takes to migrate X amount of records is the same time that it takes to validate X amount of records. If migration takes 10 hours, this is also going to take 10 hours. And hence, in order to optimize this time taken, what we did is, instead of running a full database scan, we chose to run this validation against just a subset of data. Okay, and what this subset of data is, discrepancies normally exist only in those records that are actively being modified while the migration is also running in parallel. So by focusing on those records that were created or updated since the start of the migration timestamp, it helped us not only optimize the time, but also ensured full data integrity. Of course, very clearly, this comes with a prerequisite where one must be able to precisely determine those records that were updated since the start of a given timestamp, right? It can be done in the with using event streams or change data capture, but whatever the method be, it has to be predetermined and implemented beforehand if you want to reduce the overall time taken for the migration. Coming to the last phase of the cutoff, post-cutoff review, that is, after we cut off the dual writes and then point everything to the target database, we generally ensure that the source cluster has no residual reads or writes, and ideally the number of connections to the source cluster must be 0. If everything was done right up until the last step, then this final check will simply be a sanity check, and this sanity check generally assures us, gives us more confidence to finally declare that the migration is complete. So we've reached the end of the talk and hope this presentation was useful. Thanks for your time.